Okay, so as we were discussing in the previous video, two states are said to be orthogonal if their inner product is zero. Of course, for orthonormality, two states are said to be orthonormal. If they are two different states, then their inner product is zero. If the inner product is between the same state, then the inner product would be one. So, as we have checked in the previous video, qubits are orthonormal. Okay. Let us see certain things mathematically so that these concepts are registered in our brain. Suppose if I am being given Ketzai to be 3 plus 5i plus 7 ket 1, 3 plus 5i ket 0 plus 7 ket 1, find dual of Ketzai. That's the question. Now, let's see what exactly Ketzai is. 3 plus 5i, ket 0 is 1, 0, plus 7, ket 1 is 0, 1. So what does it give me finally? 3 plus 5i, 0, plus 0 and 7. So what I'll be getting is 3 plus 5i and 7. This is my Ketzai. So how do I find its a dual or conjugate? Yes, I represent it using this notation, the Bra-Xai notation, which is nothing but the transpose of Ketzai. Of course, here since I have complex numbers, with respect to complex numbers, there is no just transpose. It is always the conjugate transpose that I'm supposed to be taking. With respect to complex numbers, it is conjugate transpose. Conjugate transpose. All of us are aware. Of course, many of you who would have done things on matrices would be aware of Hermitian, skew Hermitian, unitary matrices, where I'll be talking about instead of A is equal to A transpose, A is equal to A conjugate transpose is what I will tell when I am talking about Hermitian. My negative of A conjugate transpose would give me skew Hermitian, like our symmetric, skew symmetric kind of things in real plane, real line or whatever. With respect to complex numbers, here what I want to stress upon is it is the conjugate transpose and not just the transpose. Of course, transpose cannot be done for numbers. Transpose of a number is itself. Conjugate transpose of a real number is itself. But here I have a matrix or a row vector, I'm sorry, a column vector, which has complex elements in it or imaginary elements in it. So what I should be doing is, first I will be taking the conjugate. Conjugate would be 3 minus 5i. Conjugate is only for the imaginary number. Real number conjugate is itself, and I transpose it. So what does it give me is 3 minus 5i and 7. This is the resultant vector Bra-Xai. When I'm talking about the dual of Ketzai, it is nothing but the Bra-Xai, and it is nothing but the conjugate transpose. Okay, yeah. Let's see one more example. Suppose if I have, again, I'm telling you, we throughout the quantum computing mathematical part, I'll be using Ketzai only, computational part or whatever. I'll be using Ketzai. All of us are, those who are aware of Schrodinger equation, people know that Xi is used there. Okay, since quantum computing is resultant of photonics, photons, resultant of the concepts from there, we'll be using this notation. And then Schrodinger's wave equation, everyone knows. So because of which I'll be using Ketzai throughout quantum computing, usually by default. 3 plus 5i get 0 plus 9 get 1 is what I have get xi to be. Of course, another one I'll be taking, which is get phi, which is nothing but this vector 5, 7. Why I've given two different notations is initially only this notations scare us. Once our hand becomes free with the notations, things are not that complicated as they appear in quantum. So what I'm asked to find out is the inner product between ket xi and ket phi. What's the value of it is the question. So how do I do it? First, I will rewrite the vector notation for ket xi by expanding it in terms of ket 0 and ket 1. 3 plus 5i 10 plus 901. So the resultant is 3 plus 5i 9. Of course, again, I'm sticking on to trivial vectors only, just to make you just to shift your focus from the hectic calculations to the easy understanding of the mathematical concepts in quantum. Okay, so I understand what is ket xi. I am supposed to be finding ket xi only here. Okay, just a second. Of course, I have not discussed the outer product yet. So let us do the, this is the notation for outer product. So I'm asked to find the outer product. I've not yet discussed inner product. I've not yet discussed the outer product. So let's find the inner product. So what is the dual of ket xi? Dual of ket xi is just the conjugate transpose. I denote it by cross. Conjugate transpose of ket xi. So it is nothing but 3 minus 5i 9. Of course, I can write transpose here and then finally write 3 minus 5i 9. Next, I should be finding the inner product. Just see here, if you split, things are very simple. Of course, it needs a bit practice not to make errors with the notations. Ket xi, no, bra xi, ket 0, ket phi. Bra xi is nothing but 3 minus 5i 9. Ket phi, it's been given in the problem 5, 7. So I just multiply. Of course, as I have said, it would resultant would be a number. 5 3 is 15 minus 25i plus 9 sevens 63. So what I'll be having is 78 minus 25i is the resultant of inner product between ket xi and ket phi. Okay, now of course, let me, since I have written something, let me do with the outer product as well, but let me finish checking orthogonality as well, orthogonality between vectors as well. Let's take one more example. Suppose if I have a vector A, if I have a vector A given by 2, 4i and vector B given by -1 3i and I. I'm asking you to find whether they check whether they are orthonormal or not. Check whether the vectors are orthonormal. Of course, the question can be like, check for the normality as well. Okay, so what do I do is, of course, there is this 4i as well. Okay. So for this, what will I do? I will be going with the inner product between ket A and ket A. So it would be 2. But let me write again, because initially I need to go with the split so that everyone understands. Bra A, ket A. Of course, bra A would be 2 minus 4i. And bra B would be minus 1 minus 3i minus I. Conjugate of a complex number is just the negative of the imaginary part, as all of us know, right? So 2 minus 4i, 2 minus 4i. This is 2 4 16. No, 2 2's 4, 4 4's is 16, 2 2's 4 plus 4 4's 16. Minus into minus is plus, 16 is there. And then I'll be having, there is minus only in 1. Okay, this is plus only. Okay, so I'll be having a minus here. 16, I into I would be I squared. I is nothing but under root of minus 1, guys. So I squared would be minus 1. So what happens to this? 4 plus 16, of course, into 1. Into 1 not needed because it is negative 1. So finally the answer would be 20. I repeat it. The complex conjugate of a number is nothing but the negative of its imaginary part of a complex number, of course. If there is no imaginary part, then it's a real number. So conjugate of a real number is itself, right? So 2 2 is 4. Minus 4 into 4 is 6, minus 16. Of course, I square, I into I is I squared. I is under root of minus 1. I squared is minus 1. Root goes off. Squaring on both sides. Root goes off. Minus 1 is what I'll have. So minus of minus becomes plus. And then things will turn up like this. Okay. Now coming to the inner product of B. What it is the dual of B, ket B, I'm sorry. Okay, so what's the dual? As I have written here, the dual is minus 1, minus 3i, minus I. Minus 1, 3i, and I is the original vector or the state. So what I will be having is 1 and minus 1 into minus 1 is 1. Like previously, it is minus of 3 3 is 9 into I squared. Yeah, minus of I squared. Okay, so 1 plus 9 plus 1. This would be 11. Okay, now you can have a doubt. What would be the norm? Because when I'm talking about orthonormal and things, how do I denote norm with kets? If you have a doubt, the definition goes like this. Norm of a state or a ket would be given using this formula. Suppose of a state, let ket xi be given, then norm of ket xi, just see here, norm as we denote same thing, but then again ket xi is also there. That's the only thing. That's the only thing that makes things complicated. Look complicated. Okay. It's nothing but under root of the inner product. Okay. Shorthand notation. That's why I'm not writing two lines. Actually, if you see the split, it is just the two lines. Okay. Where the dual, the product of the ket and its dual are being taken. And the inner product. Of course, outer product is also similar, but it results in a matrix. Okay. Norm of a state is given using this formula. Then how do I normalize? Normalize a state. How do I normalize a state? Simple. The state by its norm. Ketzite by its norm gives me the normalized state. Now, normalized state is how do I write? I write like this. Of course, we can just check examples on it in the next video. Okay, I'll just stop this video here.